Okay, example 1 in lesson 1.2. We're going to match polynomial function with its graph. So we're going to look at these polynomial equations. We have A, B, C, D, and we're going to talk about their characteristics, their local max and min, their x-intercepts, and then connect them with the graphs below. We're going to match them up.
You can just use the intercepts to match them. Like the +1, the y-intercept is always going to be 1. And you can figure out that's graph number 4. And then you can do the exact same thing for the rest of the 3.
Okay, so one thing we figured out is that we can just look at the equation and right away we can identify the y-intercept. So for f of x equals 2x cubed minus 4x squared plus x plus 1, we right away figured out that the y-intercept is 1.
Yep.
Because the y-intercept occurs where x equals 0. So if this term was 0, 0, 0, if x was 0, then f of x would be 1. So your y-intercept is 1. Good. Let's carry on with this anyway. The number of max and min points, well, what other key features can we talk about? This equation, is it positive or negative? Does it open up or down?
It opens down, so that's negative.
Well,
I think.
let's look at the equation rather than the graph, because you might have got your graph wrong.
Oh, I was looking at the wrong graph.
Okay, so leading coefficient is positive.
Yeah.
Leading coefficient is positive. Therefore, opens up. Which means it extends from quadrant, well, it's a cubic, right? That's helpful. It's a cubic that's positive. Therefore, it goes from Q3 to Q1. So which graph does it match? From Q3 to Q1, it's got to match graph number 4. All right, B. B is g of x equals negative x to the power of 4 plus 10x squared plus 5x minus 4. Key characteristics. What do we know about the degree? What degree is it?
It's 5th degree, which is odd, so it's 3 because that's the only other one with an odd.
Okay, so it's not actually odd, so it's 4th degree.
It's 4th degree.
4th degree, I
I
know.
was looking at B, I was looking at C.
Yep. B, okay, so degree,
Okay, that makes sense.
4th, or
If it's negative and even,
quartic,
it opens down.
and it's negative, okay, leading coefficient is negative. Therefore, opens down. By the way, I made a mistake over here. That means because cubics don't really open up or open down. They move from quadrant 3 to quadrant 1, but it doesn't open up like that per se, whereas an even degreed function could. What else do we want to know about this thing? End behavior. End behavior, where is it going from? Quadrant. If it's a negative quartic.
It goes from quadrant 3 to quadrant 4.
Thank you.
A.
Very good, very good. So which graph is it? Or do we know the y-intercept? Let's do the y-intercept as well. Jake, do you know the y-intercept of this equation? Yeah, -4, good job. And so which one are we matching here? Graph 1, thank you. Some other things we can talk about here are how many x-intercepts do you see in that graph? How many x-intercepts do you see? Okay, so we're going to make a couple of connections here. We've got 4 x-ints and its degree 4. Okay, we're going to make a note about that later, but just kind of keep that in mind right now. How many maximum points? How many... yeah, how many maxes? Like absolute maximum. We're looking at graph number 1.
There's 2?
So there are 2 local max. There's only 1 actual max, right? There's 1 highest point on that function. Any mins? Like absolute mins? Or does it go all the way to a negative infinity? So no min. Okay, what about local max?
2?
2 local max. Local mins?
1?
1 local min. Okay, you could even label them if you wanted to, if you're not quite sure what we're talking about.
Is there a better word than local min, or is that?
Local just means there's some interval in which you could find a minimum. But if you took the function as a whole, you cannot find any minimum.
Alright, yeah.
So you've got 2 local maxes, 1 absolute max, maximum for the whole function, and 1 local min. Good. Okay, so notice that between the local max and mins, there are 3 total, which is 1 less than the degree. Okay, so the graph of a quartic can have up to 3 local max and min added up. Okay, we could do the same thing if we went back to A and we looked at its graph. Looks something like this. It has a local max and a local min for a total of 2, and its degree 3. So the most ups and downs it can have, the most high and low it can have is 2. 1 less than its degree. Good. Gonna do the same thing for C. Now that we're getting the hang of it. H of x equals negative 2x to the power of 5 plus 5x cubed minus x. What is the degree? What is the name of this thing?
It's 5th degree?
It's 5th degree, so it's a quintic from our chart from yesterday when we named all these things. Leading coefficient, positive or negative?
It's negative.
Okay, so now we have enough information for its end behavior. It's odd, so it's going to start and end going different directions, and it's negative. So what are our quadrants that we're going to extend from and to?
Q2 to Q4?
Yes. It's going to head kind of down. Whatever it does in here, it's going to be heading down. Somehow it's going to be like that. Right. All right, let's identify which picture it matches with. From Q2 to Q4, there's only one that does that. Graph 3. And now we're looking at the graph, and we're going to make some comments. How many local max and min are there?
There's two local maxes and two local mins, but there is no absolute max or min.
Thank you. Okay, and again, we can note that if we add up the local max and mins, we get 4, which is 1 less than the degree.
Is that every time?
It doesn't have to have 4, but it cannot have more than 4.
Okay. Yeah.
So, for instance, something to the power of 5 can only have 1, 2, 3, 4 bumps, max. 1, 2, 3, 4.
Yeah.
So if it has that, you know it's not a cubic because it has too many bumps. Too many local max and mins. Good. Carry on. D. D is P of x equals x to the power of 6 minus 16x squared plus 3. What is the degree? Wow, well, then just give the number. 6th degree, sure. Perfect, 6th degree. We don't have that name in the chart, so we just use numbers beyond that point. Good, leading coefficient? Positive or negative?
Positive.
And it's even function, so we can tell if it opens up or down. What does it do? Opens up. Thank you very much. Which means we know it's end behavior from quadrant
Quadrant 2 to quadrant 4?
close.
2 to 1.
2 to 1.
I'm looking at one graph.
We haven't even picked the graph yet. You can't be looking at a graph yet. We're doing this all just from the equation.
Okay, sorry.
Now you can pick the graph. Which graph should you be looking at?
Graph 2.
Graph 2. Thanks very much. All right, let's talk about the local min and max of graph 2.
Local min and max?
Mm-hmm.
There's one local max and two local mins that are probably both the same absolute minimum.
Yes, that is true. Okay.
It's pretty interesting.
What else do you notice about that graph? What is interesting or unique about it?
Symmetrical.
It is symmetrical. Okay. It is truly even. Let's see if you can do this. What is special about its equation?
All the powers are either 0 for x or even. There's
Okay.
no odd powers.
Thank you. All
That's
of the
what I'm trying to
powers are even. So this is x to the power of 0, right? That will create a symmetrical graph.
Wait, so if all the powers are odd, do we get actually no, never mind.
Then you would have point symmetry. Yes.
Oh really? Oh okay, yeah. We would.
It's a beautiful thing. Okay. Good. Let's carry on. We've done enough there. Thanks, team. So at the bottom of that, we take a couple of notes. You have space on the bottom of page 9 for a few notes, which is something you've heard about before, but it is finite differences. And we're going to make a connection today that's going to allow us to use finite differences to actually determine the leading coefficient within a polynomial function. So finite differences, and here are your notes. For a polynomial function, for a polynomial function of degree n, so that's the exponent, right? The exponent of, it's the highest power of x, degree n, where n is a positive integer, so a positive whole number. The nth difference, the nth differences, just to give you some context of what we're talking about, you're probably familiar with, let's say you had an x, y chart, and the numbers here were 1, 4, 9, 16, 25. Hopefully that's looking a little bit familiar. You would calculate the first differences. It's the difference between y2 and y1. So you'd go 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. 25 minus 16 is 9. That is the first differences. Okay? Then we would get the second differences. 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. And once we had a constant, such as 2, 2, 2, then we'd be done. Since it's the second difference, we would know that it was a quadratic with degree 2. Okay? That's something we've done in the past. Okay, so this is going to repeat that and then extend from that. So the nth differences are
Constant.
equal.
Oh.
Or constant. Yeah, we'll say constant. That's and I'll just do or equal in brackets. Okay, so that's what we just talked about. If the second differences are constant, then we know it's a quadratic. If the first differences were constant, we would know it's linear. If the third difference is cubic, fourth, quartic. Okay, carries on that way. Here's another thing that's interesting. The differences, so in this case 2, 2, 2, they have the same sign as the leading coefficient. Have the same sign as the leading coefficient. Okay, so your differences, depending on the function, okay, this was clearly just simply y equals x squared is what I did it based on. But you might end up with the constant differences where the differences are negative value. Okay, that would mean the leading coefficient of the polynomial, even if you didn't know what the polynomial is, you would know that the leading coefficient is negative, which means you would know the degree and you would know if the sign of a leading coefficient. So what else do you know?
You know where Q2 and Q, right?
You know its end behavior.
End behavior. Yeah.
Yes, you know its end behavior. You know if it's even, if it opens up or opens down, and if it's cubic, you know if it goes off this way or goes off that way.
Negative, its end behavior would be negative, right?
You could say it that way, yes. You would know that the leading coefficient of the polynomial is negative.
Yeah.
Yep. Okay, third thing here. Here is another interesting thing that we're going to be using quite a bit. The nth differences are equal to a, and then in square brackets, n. I'll explain it this way and then I'll explain it the other day. Times n minus 1 times n minus 2 all the way to times 2 times 1. Close that square bracket. I'll explain what this is in a second. Where a is the leading coefficient. Okay, so what does this whole thing even mean? Basically, what it means is that you can take, remember the function is the nth degree. So this is the exponent, the highest power of x, right there, okay? A is the leading coefficient. You don't know what the leading coefficient is yet in this scenario, okay? But you do know the degree, and what this, inside this box means, n times n minus 1, which is just the number just below n, times the next number, times the next number, times the next number. Okay, so if you had a function that was like x to the power of 6, basically all it's saying is that you take 6 times 5 times 4 times 3 times 2 times 1. Okay, the symbol that represents that, or the word that represents that, it's called factorial. So when you take a number and then multiply it by one less, multiply by one less, multiply by one less, it's called a factorial. And it's represented by an exclamation mark. So maybe I'll just make a totally separate note for you here. What's happening here is I'm going to write it this way. The finite difference is equal to a n factorial. Okay? And n factorial equals n times n minus 1 dot 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 all the way until you get down to times 2 times 1.
So the finite difference of, let's say, the leading coefficient is n to the power of 6. It would be 6 times 5 times 4 times 3 times 2 times 1.
Times the leading coefficient, yes.
That's like just the expression.
So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. So you've got 20, 60, 120. Okay, that's just the factorial part.
When would we even use that?
So this is going to allow us to find out what the leading coefficient actually is, which gives you your direction of opening, gives you your stretch compression, and then from there you can determine some of the other things about the equation as well.
So the factorial.
Okay, let's give this a shot in example 2. So in example 2 on page 10 in your notebook, we're going to identify types of polynomial functions from finite differences. So each table of values represents a polynomial function. We don't know the function, but we can find out some things about it by using the finite differences from the table. So let's go ahead and take those finite differences. I'm just going to copy it down quickly. The y column, negative 36, negative 12, negative 2, 0, 0, 4, 18, 48. Okay, and to take first differences, remember we're taking y2 minus y1. So first differences, we've got negative 12 minus negative 36. Because negative 12 plus 36, that's 24. For the sake of your notes, I'm going to write it out. Negative 12 minus negative 36, 24. Okay? Then you have negative 2 minus negative 12. Negative 2 plus 12, that's 10. Then you have 0 minus negative 2, that's positive 2. 0 minus 0 is 0. 4 minus 0 is 4. 18 minus 4 is 14. 48 minus 18 is 30. Okay, it's not constant, so this equation is not linear. This function is not linear, so we'll go for our second differences here. 10 minus 24, minus 14. 2 minus 10, negative 8. 0 minus 2, negative 2. 4 take away 0, 4. 14 take away 4, 10. 30 take away 14, 16. Still not constant. Let's go for a third finite difference. I see something here. I think we're going to get it here. Negative 8 minus negative 14. That's negative 8 plus 14 is 6. Negative 2 plus 8 is 6. 4 minus negative 2 is 6. 10 minus 4 is 6. 16 minus 10 is 6. Okay, so we've arrived at a constant finite differences. We did the table of values and we determined finite differences until we got a constant. What does this tell us?
It is cubic.
Okay, so I'm just going to make a note. The third difference is constant. So the function is cubic, or the values in the table represent a cubic function. Which also just another way of saying that the degree is 3. Okay, that's 1. That's what we were going to find out when we are looking for the degree of the polynomial function. Now, what is the sign of the leading coefficient? Well, the sign of the leading coefficient is the same as the constant finite difference, same as its sign. So if our finite difference is positive 6, then the leading coefficient is also positive.
Okay, yeah.
Okay? Now the last thing that we're able to do is to determine the value of the leading coefficient. So we know that the finite difference is equal to an factorial, where a is the leading coefficient, that's unknown, n is the degree, which we now know is 3, and the finite difference itself is 6. Okay, so the finite difference is 6. We can sub that in. A we do not know, and n factorial is going to be 3 factorial. So there's two ways to do it. I could divide both sides by 3 factorial, or I could figure out first what 3 factorial is. I'm going to do that strategy. So we've got a times, and 3 factorial is 3 times 2 times 1. Okay, that's one you can do in your head really quick, but I'm writing it out so that you understand what the factorial part is. Which means on the right side we have 6 times a, which tells us we divide both sides by 6, we get a equals 1. What was a again?
Well, now we know it's 1. So.
Now we know the leading coefficient is 1.
Yeah.
Okay? Once you do this a bunch of times, it becomes pretty straightforward, knowing which piece is what. All right, that was great. I am going to clear, and you can start doing the differences on example B. So you can start figuring out the first, second, third, etc. differences. You can use a calculator if needed.
I don't understand. This is a cubic. That's why it's no, it's confusing because it goes up and down. Like 4 goes, like 3, it goes up, then it starts going down again. Once you get to 3.
Okay, at this point you can look up and copy the rest. I'm sure you got some great practice there. Some mental math. The challenge is if you mess up one number, it messes up your whole chart. So don't mess up anything. If you get into a situation where it's like -24, -24, -20, -24, then you can be pretty sure that you made a simple mistake somewhere. All right, what does this tell us? Have we identified the degree of the polynomial function?
It's fourth degree.
Do we know the sign of the leading coefficient?
$24?
Sign?
It's negative.
And how do we determine the actual value of the leading coefficient? Well, we know that FD equals A n factorial. We know the finite difference. The fourth difference was -24. We don't know the leading coefficient, that's A, but we do know the degree, which is n, it's 4. So we have 4 factorial. 4 factorial is 4 times 3 times 2 times 1. So we got 4 times 3 is 12 times 2 is 24. So on the right side of the equation we have 24a. Divide both sides by 24. We have a leading coefficient of -1. If you accidentally write 1 instead of -1, you can always double check with what you already figured out that the leading coefficient is negative because the finite differences are negative. Okay, a little double check is built in there. All right, that was already a lot easier than the first time doing it. So imagine what it's going to be like when you do it 10 more times at home tonight. It's going to just be cruising.
That's pretty funny, guys.
Okay. Example 3. Application of a polynomial function. A new antibacterial spray is tested on a bacterial culture. The table shows the population, P, of the bacterial culture t minutes after the spray is applied. Use finite differences to identify the type of polynomial function that will model the population growth, and then also to determine the value of the leading coefficient. Okay, so we're doing essentially the exact same thing. Here we go. 800, 799, I'm just doing the population column. 782, 737, 652, 515, 314, 37, and by now you probably have all your differences done already. First difference, -1. Second difference, -17. Sorry, not second difference, second number, -17. Then, uh-oh, it's getting harder. 45?
Yeah. Now -85.
Thank you. And then 63?
-137.
Ah.
I think it. Yeah.
Yep. -201. Got it. And -277. Is that right?
No, it should be 200. Right, yeah.
Yeah, it's good.
How do you do this? I don't understand.
Second differences. -17 minus -1.
16.
-16. Then I'm just going to copy out of the book for the rest of them, okay? -28, -40, -52, -64, -76. Still no constant. Let's go for a third difference.
No, -12.
-12, -12, -12, -12, -12. Excellent. What did we find out? The type of polynomial function that models it is
It is cubic.
Cubic. And we need to find the value of the leading coefficient. So I'm going to let you do that one on your own. You have the formula memorized. It only has 3 parts. FD equals AN factorial. You fill in the blanks and complete the algebra. And you can double check to see how you did on the board. Then we could use technology to determine a model for this, which we're not going to do.
Okay. Well, it's a lot of time for homework there.
Your homework comes from page 26, problems 1 through 9 and 11 through 13. Enjoy.
And coach, we could probably